time on group. We're working on the experiment 3, which will be the refrigeration cycle. So just a short introduction. In this experiment, we will analyze the performance of a heat pump, which basically the purpose of a heat pump is to absorb heat from a low temperature source and move it to a high temperature source. Some objectives, including just learning how to perform a thermodynamic analysis of said heat pump, learning how to measure the coefficient of performance, and learning how to describe the vapor compression refrigeration cycle in a pressure and enthalpy diagram. Just some theory of it. The coefficient of performance is defined as the ratio of the magnitude of the desired commodity to the magnitude of the expenditure, which is just the simple equation for any efficiency. In the case of the refrigeration, it is the ratio of the amount of work that is put in to the amount of refrigeration that takes place. In order for us to calculate the coefficient of performance in the refrigeration unit that we have, there will be pressure and temperature transducers at various locations around the loop, and using the results from those transducers, we can calculate the enthalpies, which are in turn used to calculate the coefficient of performances. Just some more theory. One of the main the second law of thermodynamics states that heat naturally flows from hot to cold. So in order to get heat to flow in the opposite direction, you must add work in. And a simple, these are just some of the derived equations for the coefficient of performance for cooling specifically. That is the heat rejected from the cold over the heat added minus the heat rejected. And that's for the actual cycle. For the ideal cycle, it simplifies to just the cold temperature over the hot temperature minus the cold temperature. And again, QH should be transferred to hot. This is the depiction of an ideal cycle versus a real cycle. This is the ideal cycle. You can see that for the heat rejection and heat addition parts of the cycle, it's at a constant pressure. For the compression, is a constant entropy, constant entropy compression, and for the throttle, it's assumed to be adiabatic in that no heat is added in this process. But compared to a real cycle, it's shown that whenever the heat is rejected and added, the pressure is not constant. This is due to just friction, temperature changes in the components themselves will cause the temperature to drop. The compression itself is not assumed to be completely isentropic, and when compressing whatever fluid you're using, some heat will get added. And also, one thing is that the compression almost never occurs exactly with a saturated vapor. The vapor is always somewhat superheated, and then the subcooling almost never occurs for a saturated liquid. It always goes past and then eventually gets back into the vapor dome. This is the apparatus we're going to be using. The primary components are, as shown, the condenser, evaporator, a liquid separator to separate the saturated liquid and gas. There are some pumps that will move the working fluid to and from the condensers and evaporators. There's an accumulator, which again filters out some saturated liquid and gas. And in the case of our specific refrigeration unit, R134 is used as the working fluid, and the two temperature control pumps move water from the reservoir to the evaporator and condenser. This is a procedure. It's pretty simple because the unit itself is already set up and there's not much for us to actually do. All you do is you would start the software, you would switch on the pumps so that the evaporator and condensers are both operating, and you would set the water flow to be at 5 liters per minute. You switch on the compressor and set it to an approximate value of 40%. You will wait for the system to become stable, and using the software, it will measure the values indicated. Well, you will measure and write down the values in the table that is provided to us in the lab manual, and then you write down the obtained values. There's a little bit more. So for the tests themselves, for exercise 1, you're just going to determine the inlet power, produce heat, and coefficient of performance. For exercise 2, there will be a layout of the vapor compression cycles in a pH diagram, and you will compare that with the ideal cycle. So for experiment 2, you will perform it at 3, 4.5, and 6 liters per minute, and then compare the values that you would get to what values you would get from an ideal cycle. Just some general lab safety tips. Always wear appropriate attire, so long pants, closed-toe shoes, safety goggles. Follow the directions closely and carefully, and always return all equipment and instruments to the original location once experiments have concluded. That's no reference. Any questions? Yes.
Can you talk about some sources of error that could happen during this experiment?
Again, there shouldn't be too many because, again, there's not much for us to set up. All you have to do in the procedure, we just start the pumps, switch on the compressors. Maybe you could have the wrong, flow rate would have an impact on the measurements that you would get. So having incorrect flow rate would skew your results a little bit. But apart from that, there shouldn't be too many sources of error.
Thank you.
Yes.
Can you go back to the ideal and the real cycle?
Yes.
Yeah. So the left chart is the ideal? Chart?
Yes, because they're constant pressure. Well, the cooling and heating occur at constant pressure. The compressor is considered to be isentropic, and this would be this expansion valve, which is considered to be adiabatic.
So for the heater, I mean 3 to 4.
Oh, this is just for cooling. Sorry.
Oh, okay.
Yeah, this is our refrigeration cycles. It's a bit different for heating cycle. And this is also specifically for the vapor compression refrigeration cycle.
All right, I think that's all.
Okay.
Thank you, Chris.